set up the, review everything so far from the Kepler problem. Try to put it all there and then we'll continue on. So, this was the Kepler problem. And we got pretty far. So I just want to put up all of those results. So let's just list everything here. So we're looking at the central force problem in this form. I won't put the reduction from two bodies to one body. Okay, so that's a reduced mass and it's a two-body problem. And then we get a potential energy of this form. And with this and with conservation of angular momentum, so that would be R cross M R dot equals constant. So with these ingredients, we find that motion is restricted to a plane, so then we use plane polar coordinates, and I'll even write that down. Just have everything here. Y equals R sine of phi. Then we write the energy down in this form. R dot squared L squared over 2 mR squared plus U of R equals E. And this is the effective potential as a function of R. And we had the conservation angular momentum gave us mR squared phi dot equals L. So that went into this thing right here. Then we went ahead and did the quadrature here. And using these two expressions, we ended up with, I think from here I can cut to the chase. We ended up with R equals P over 1 plus E cosine of phi. So that was the equation of the trajectory, right?
Yeah.
And we needed the, and these you may have to remind me of, this was L over M alpha, or alpha squared?
It's L squared over M alpha.
L squared over M alpha, good. And then that's the parameter, and then the eccentricity was the root 1 plus 2 E L squared over M alpha squared, I believe. So that's when you have.
Yeah.
Great. So it turns out, so then we started to analyze all this. Okay, there was a bunch in here, and actually that integration we did, I was going to assign as a homework problem, just to repeat every step. Okay, so we'll talk about that a little more. So this is the polar form of the conic sections, and so our work has just begun. Polar form of the conic sections. So it contains ellipse, circle, parabola, hyperbola. Okay, then the analysis that we started, we showed that, so we find P equals R0 equals the radius of circular orbits. And we found that by just saying, okay, when E is equal to 0 here, then we have a constant radius, so that's a circular orbit. So we found that, and we also found that if R is equal to R0, or this P right here, E is equal to minus N squared over 2L squared. And that's the energy of the circular orbit, and that's the minimum of the effective potential. So R0 equals minimum of U effective of R. And then the corresponding energy was that U0. So that was a complete consistency check. And then we started working on the ellipse itself. And I want to make a pretty big picture. Yeah, I'll make the picture right here. So that we're working on the trajectory. And it's hard to draw a nice ellipse, but you got something like that you can label. You've got the semi-major axis, the semi-minor axis, and I think I left us where we wanted to know this little distance here to the center. Would this be the last thing in your notes?
Yeah.
More or less, yeah. So let's remind ourselves, what are these quantities? So A is P over 1 minus E squared. B is P over root 1 minus E squared. 1 minus E squared. And so, and these points here, this point here is E is equal to 0, P over 1 plus E. And this point here was P over 1 minus E, plugging in phi equals 0 over pi. Okay. And so what we have here, okay, so here we go. So in order to find the geometric center of this ellipse here, we're just going to do the following calculation. So to find D, we're going to do this magnitude D. So we're just taking this length as a magnitude. D plus P over 1 plus E is going to equal that A, right? 2A down here equals A. You can equal P over 1 minus E squared. So that'll a little bit of arithmetic ought to get us there. So D equals P 1 minus E squared minus P over 1 plus E. Multiply 1 minus E on the bottom. Just a common denominator, 1 minus E squared. P minus P plus E. So P 1 minus E squared equals E times A. So that's not bad at all. So this distance here equals E times A. When the eccentricity is 0, then you've got a circle around this origin. Otherwise not. I think now we have a fair collection. E equals E times A, and A is up here. So now we have most of what's going on. And let's make sure we formulate what we wanted to do last time. Yeah. Now everything's on the board. Good. So yeah, those homework problems from last time, now I'll formulate them. What am I going to erase? I'm going to erase this stuff right here. Yeah. So what we wanted to do, and I'm just repeating what I had last time, but make sure make this clear. So the first thing we want to do is repeat the entire calculation. Just write it out and make sure we understand every step. Leading up to this expression right here. Okay. Up to, r is equal to p over 1 plus e cos p. So there were a bunch of interesting steps there, right? And you should have them all in your notes, and you can find them all, and you just want to go through every single one. And you can literally start at these points here, right? You can start with the derivation of what goes into this expression, several lines, but it'll take you here, and then you have to do that substitution, and you'll follow it all, and then you'll do those integration substitutions and so forth. Okay? Because it's a lot to see at once, right? And to actually be able to do it, and then you'd be able to knock it out without even any notes, and you have it down. Okay, so this is an important one because the Kepler problem is such an important problem in physics that if we, this is the first time we've actually done something this rigorous. Because you've seen this kind of thing, physics 4A, but it was just the statement that it's an ellipse. Here we actually are proving everything. So that can't be overstated. So we're proving everything, and the other thing we're proving is show that this polar form of the ellipse agrees with the ellipse that we know, which would be x plus b squared over a squared plus y squared over b squared equals 1. This is the old x squared over a squared plus y squared over b squared equals 1 ellipse, except since it's shifted, we had to have the x plus b, and b's that positive quantity. But I'll warn you, this calculation is just a bunch of algebra and trig, and sometimes people find a quicker way to this solution, sometimes they go in circles. Okay? But what you'll find when you plug everything in here, I'll even get you started. So basically, your x is this r cos phi, right? So you have p times, so let's write it out. So x is r cos phi, so that is p cos phi over 1 plus e cos phi, right? And then the y of r sine phi is p sine phi over 1 plus e cos phi. And you're plugging all these definitions in, and you're really just trying to show that this all equals 1, or if you subtract 1 from it equals 0, right? It's just a big identity. And when you get there, you'll know it. Okay? So there's a couple different strategies to effect that. One thing you'll notice, these things are all proportional to p, right? In the numerator and in the denominator. So those, for example, p will cancel right away. We can set the thing up. E on the other hand is dimensionless, and that'll hang around. Okay. So good. Having done that, then we've shown Kepler's first law. Okay, that the orbits of the planets, ellipses with the sun at one focus, and of course it's much more general than the sun and planets. It's any mass and any object that happens to be orbiting it. So of course it's Kepler's second and third law. Now I have to tackle as well. Make sure we got everything up here. Yeah. Okay, so you guys will do this, and then we can declare victory on this problem. For Kepler's second and third laws, though, we have some interesting stuff. I'll show those next. topic should reveal Kepler's second law to us. And what we're just gonna do is look at the angular momentum. In the central force problem. So we have m r squared v dot is equal to a constant. So we can look at is imagine this is a section of the trajectory, and this here is d phi. This is r d phi. So then what we have is an infinitesimal area, named the area of that little triangle, that little wedge there, which is part of the orbit. So dA is equal to 1/2 r squared d phi. So the area that's being swept out is going to be dA dt equals 1/2 r squared d phi dt as the planet does its orbit equals 1/2 r squared. The d phi dt is L over mr squared. The r squareds cancel. And we have dA dt equals L over 2m. Make sure I get that r squared d phi L over 2m. That's right. Equals a constant. So this actually is Kepler's second law. So what we have is the rate at which area is swept out is constant. So area swept out at a constant rate. At a constant rate. And if you're, say, looking at a nice exaggerated ellipse, what you'd be saying is this area is the same as this area here. Okay. And that was Kepler's second law. So you notice Kepler's second law didn't even make use of all of this formalism. It really just made use of angular momentum. But angular momentum hadn't been discovered or invented at that time, conceptualized. So the Kepler second law is actually the conservation of angular momentum through an orbiting planet. And Kepler's second law was equal areas in equal times. So I'll put that here just to make sure we have that. Equal areas in equal times. That was Kepler's second law. Of course, it means that when you're closer to the center of attraction, here, this side, you're closer, you're moving faster, you're farther away, you're moving slower. By the way, for our planetary system, anything you draw by hand is going to look like a circle, or at least for the inner planets. But the data were good enough back then that Kepler had to, we couldn't sweep it under the rug. Couldn't say it was uniform, couldn't say they were true circles, even though they looked like circles if you just draw them. So good, that would be Kepler's second law. So make sure we have that, that's the second law. Okay. And then we'll get to the third law. Do we need this up here? Doesn't matter. We have that. We have those two homeworks. Actually, I do need some of this stuff. Let's see. see if let's clean this up here. Okay, so the third law is the law of periods. So, third law. That's the one that we inserted into, that's the one we used to derive Newton's law of gravity, or to motivate it. Law of periods. And we're going to use this formulation right here. So we have period of orbit. We can actually use this expression here. So period of orbit t, and what we'll say is the area of the orbit is equal to the integral of this area being swept out from 0 to t. Okay, so that's the area dA dt dt swept out in one complete orbit of period t. So here we would have pi times a times b as the area of this ellipse. And on the other hand, we would have dA dt, which we know is a constant right here. So this integral is trivial. It's this constant L over 2m times the period itself, because this being a constant, 0 to capital T times the period itself. So what do we have here? T is equal to 2m over L pi times A, and this B is related to A in the following way. We take the square root of A and multiply it by P to the 1/2. Okay, if we take the square root of A, we have square root of A is square root of P 1 minus E squared. The square root of 1 minus E squared, and then we multiply it by P to the 1/2. Again, that gives us P. So this is already 2m over L e to the 1/2 pi over L e to the 1/2 pi a to 3m's. You could actually already call this Kepler's third law. Squeeze this right in here. But Kepler's third law was period squared proportional semi-major axis cubed. And you see we have that, right? If I square this, I have a cube over here. But we're not quite done. We want to clean this up a bit. Was, what did we have there? L squared over m alpha?
Yeah.
L squared over m alpha, good. So if we go into here, t squared, we're going to have 4m squared over L squared. Then the p to the 1/2 is going to be squared L squared over m alpha, and then pi squared, and then a cubed. You can see this simplifies a bit. L squareds are gone, and do a little more consistency check on this thing. Okay, make sure we got it right. And then we have a really nice, problem that will go with this thing as well. So, check, so we'll just write check. So if we do a circular orbit, then as you guys remember, we had G N M over R squared is equal to M B squared over R. So we had Newton's law here. These cancel. Let's just keep going. M 2 pi squared over T squared R pi squared. Oh, sorry. Pi R squared. R. And then the T squared proportional to R cubed. So R squared over R, we're going to do this right now. And the T squared proportional to R cubed. So we should have M 4 pi squared R cubed. And then that alpha. Okay, let's see what that turns out to be. So these cancel. These cancel. And then the R squared. That equals alpha over R squared. And, I'm missing a power of M here, hold on. Oh, this is good. You know, we've been using that U of R is equal to minus alpha over R. Right, we use that on our entire calculation. And of course, this was GMN over R originally. Right, we just substituted that for simplicity. Okay, good. So we've got the check of that and the circular orbit as well. Okay. So we have this, and this one's important, so we're gonna hold on to this. So there's an interesting assignment we did earlier on in the semester. You guys remember the time it took for a point particle to fall into a center of attraction? 1 over R squared law, 1 over X squared law originally. We're gonna find a limiting case of that. I'm gonna set that thing up. We're actually gonna repeat that whole calculation that we've all done. So yeah, it's important that we get this one right, and I think we have this one right. Yeah, this is perfect. Okay, let me go ahead and erase some of this. Okay, so we have all of Kepler's laws now. So that's the big triumph of classical mechanics so far, was to duplicate those laws of planetary orbits. Now we want to do something with this third law, and I just checked it out for the circular orbit. Yeah, I'm going to erase all this stuff and we'll just reconstruct it. You can tell me what we have off my notes. Let's see what we do here. Okay, let's start out with a fresh board here. So for the Kepler problem, we now have first law, ellipses with the sun at one focus. Orbits of the planets. Okay. For the second law, we have equal areas and equal times. And for the third law, we have t squared proportional to a cubed. That's a semi-major axis. This is the one we're going to work with again. So we call the homework problem and that problem was for u equals minus k over x. We were to find the time it takes for a particle to fall into a particle at distance L to fall into a center of attraction. You guys remember that one? Ever so vaguely?
Yeah.
Because we were starting to do those quadratures, right? Separation of variables. So there's a relation on that one. So homework problem for you. Let's make sure we write your time to fall into center of attraction. And the idea was you were released from rest here at distance L, and then you were attracted and fell into the center of attraction. So what's interesting about that is that we also found the t squared proportional to L cubed law. So let's just set this one up again. We're going to use these letters, and then we'll relate it to Kepler's law of periods here, which is pretty interesting, and it should cover it exactly. Okay. So at the time we had the following. We had 1/2 m dx dt squared plus u of x, which was negative k over x, equals e, which was negative k over L, because we were releasing it from rest. We're releasing it from rest here, so the total energy was potential energy negative k over L. And we had to do the quadrature, so we had dx dt. We're just going to repeat this one, by the way. Nothing wrong with that. 2 over m, 2k over m, 1 over x minus 1 over L. So we had dt was equal to plus or minus dx 2k over m, 1 over x minus 1 over L. And what we did was integrated this up. And instead of capital T, I'm going to use tau. Just so we got this time to fall in. And basically we were starting from x equals L. We're going to x equals 0, and we are therefore taking the minus sign. So the integral we get off of this, we end up with tau is proportional L to the 3/2, okay? Which is just like Kepler's law. But what's the relation of this problem to these ellipses? Okay. This is just a straight line. We're falling into the center of attraction of a straight line. And of course up here, we were looking at those ellipses. So we're gonna reconstruct this. And the homework is gonna be to reconcile these two. And it's a pretty satisfying thing. We've done this before, so you just repeat this one, make sure it comes out again. So how do we so let's compare to, I'll just call it the Kepler ellipse. Kepler ellipse law of periods. So what did we just have up there? Somebody picked that up. What did we just have for the Kepler's third law? The actual letters.
M over alpha,
M over alpha,
parentheses 2 pi squared.
and then A cubed?
Yes.
Great, okay. So that's the period, you know, if you take the square root of both sides, you know, A to the 3/2. And here we have an L to the 3/2. So this is interesting. To reconcile these two, we need to think of ourselves having a very eccentric ellipse. That picture, but let's get those labels up here. Because we know we've got D equals A times E. We have, this is 2A over here. This is 2B. And A was P over 1 minus E squared. And B was P over root 1 minus E squared. So what we're looking for is an ellipse that is just progressively flatter. Mathematically, we want an ellipse that is super flat and it's doing this. Okay. Because then the period of the orbit, or put it this way, half of this period will be the same time as falling into the, okay. So first of all, we have to see, is this possible? Are these really eccentric orbits going to just come in here and whip around? In fact, in the limit, as B over A gets sufficiently small, it's almost as though this thing is coming in and colliding, except it's not colliding, it's whipping around and zooming out there. With a real planet, you can't do this because you're more than just a point in space, okay? But let's have a look at this. So what we need is, we need limit B divided by A goes to 0. That's the idea. Okay, it's supposed to get really flat compared to its length. And B over A is equal to P over root 1 minus E squared. And then we have P over 1 minus E squared. So the P's cancel. We have 1 minus E squared over the root 1 minus E squared equals the root of 1 minus E squared. So apparently as E gets arbitrarily close to 1, our trajectory gets arbitrarily flat. Good, so that's possible. Okay, everybody see that? Good, right. So now, what can we say about A here? You see, 2A was always from this side to that end. So now we can say that this, in the limit, as B over A goes to 0, which we can do as the eccentricity goes to 1, then A and L are the same thing. In other words, we're zooming around here, coming in and then leaving again. So now A approaches L from that previous problem over here, right? And T, I'll just write Kepler, is equal to 2 times that tau here. Because the period of the orbit is the time it takes to fall in and then to return out. Okay. So that's what you guys want to make sure is true. Okay. So you do this calculation, you identify what this K was, it was the same as our alpha. Right. And so the homework is to show this. Verify it, make sure it's true. If it's not, we're gonna have to rethink it. Someone made a mistake. So yeah, that's an interesting limiting case of the Kepler problem, of the Kepler ellipse, that you can have these arbitrarily flat curves. One of our colleagues here who retired was doing work using this for the hydrogen atom, for certain states of the hydrogen atom, but for the semi-classical, like the Bohr-Sommerfeld model, is actually using this fact here. Very interesting. Let's see what else we have to say about this. That's good. So that actually makes a nice problem set for this week. Did we have anything else? We didn't have anything else for this week so far, right?
It was just the 2 questions you,
The ones I reviewed today?
yeah.
Yeah.
The one you gave more information on.
Yeah, those two, those are good. Okay, so you'll have a really great set. And then this one here is an interesting problem. I have one more idea to complete this part of the discussion. So, yeah, this should, yeah, you can see that. So, let's see. This is good, goes to 0. Yeah, let's make sure that we note here, as E goes to 1, eccentricity goes to 1. That's the other opposite of that in the case. Okay, good. So yeah, there's one more thing we actually have to have. I made use of the fact that the area of an ellipse, I call it capital A, pi times A times B. I'm gonna have you guys prove that as well. That's a very simple math problem. And then we'll have really done everything we have to do on this, right? We'll really have demonstrated everything necessary for the Kepler problem. Okay, you guys have this. I'm going to erase this here, and we'll quickly prove the area of the ellipse. I'll just set that up for you guys. So the last of these homework problems, so there was that one, and then homework, prove that the area of the curve, the area bounded by x squared over a squared plus y squared b squared equals 1, prove that area bounded by this equals a equals pi ab. And what you do here, you've got your ellipse. This time it's centered on the origin. Don't worry about that. That's just the natural way to look at it. Okay, I'll draw your ellipse first. Okay, so good. We've got A and B And what you can do for this, you can even just take the first quadrant. You can say, y squared over b squared is equal to 1 minus x squared over a squared. So y is equal to b root 1 minus x squared over a squared. And say you integrate this in the first quadrant. So then area over 4 would be integral 0 to a dx, and then this b minus x squared over a squared. No. Dx, b root 1 minus x squared over a squared. 0 to a. That'd be a over 4. And then you just do a substitution. Let y equal x over a, dy is dx over a. And you already see then your a over 4 is equal to, dx is a dy, and I have b already, so b a dy root 1 minus y squared. Okay, so here we go. The area bounded by the ellipse is 4ab integral 0 to 1 root 1 minus y squared. I'll leave the rest to you. You're just going to find that first quadrant, it's the first quadrant of a circle, it's going to be pi over 4. Okay. It's the first quadrant of the unit circle. But yeah, go ahead and take it from the top here, and then, work your way through. Then we really have done everything on the Kepler problem. That should be pretty satisfying. So that'll make a good homework assignment. That way you just go over everything that you possibly can. Yeah.
I have a question. How come we're integrating from 0 to a instead of 0 to pi over 2?
Here?
Yeah.
Oh, here, because we basically just solved for y of x from this definition here. And then so the integration from 0 to a is just giving us that area right there. Right? Along the x-axis. That make sense?
Yeah.
Yeah, because we're not actually, good point. So we're not in any kind of polar coordinates right here. We're just in Cartesian coordinates. And then this little coordinate substitution, I mean, if you were to look at this and say this is the first quadrant of the unit circle, you could declare victory right there. Because we've done it before. But anyway, we used it for Kepler's second law, or third law. So, Kepler's third law, so yeah, we have to make that up, and then it would be a dy. Yeah. Good. More to come on the Newton's law.